Hello everyone, it's Dr. C. The topic that I'd like to cover in this video is formal charge. And let's just first talk a little bit about what it is, and let's just do a number of examples. Okay? So formal charge is not a real charge. The name kind of implies that. It's really kind of a fictitious charge that we assign to each atom in a Lewis structure. So again, we're going to work from Lewis structures. We're going to assign this formal charge to each atom. And where we use this most often is if we're a little bit unsure about what might be the best structure. Okay, we can compare a couple of different structures in terms of formal charge. The one that has formal charges closest to 0 is the best structure based on formal charge. It may or may not actually reflect the true structure of the molecule, but in terms of formal charge, the best one is formal charge is closest to 0. All right. So what do we do? How do we assign this? So let's look at the second statement here. The formal charge of an atom is a charge it would have if all bonding electrons, so we do count non-bonding, we'll talk about that, were shared equally between the bonded atoms. So if we have a single bond, that's a 2-electron bond, we're going to split the electrons up equally. Same for a double bond, same for a triple bond. We ignore any difference in electronegativity. We just split them as if the electronegativities were equal, and we give equal numbers of electrons, bonding electrons to each atom. As we work some examples, this will become more clear. So, and then we're going to calculate a formal charge based on the number of valence electrons that atom has versus the electrons that we count for it in that Lewis structure. Okay? Let's work some examples. So keep this in mind. It's not a real charge, but it allows us to compare valence electrons to what we assign to it in the molecule, and we don't worry about electronegativity. So in my part 2 video on Lewis structures, I drew the Lewis structure for sulfur dioxide. And we came up with this structure. Okay? So if you want to go back and review that, this is Lewis structure video part 2. All right? And this is just one of the 2 resonance structures that we drew. So there's a second resonance structure. All right? Now, quite often, however, you will see the structure of SO2 drawn like this, with 2 double bonds. And sulfur exceeding the octet rule. Now, sulfur can exceed the octet rule. It is in the 3rd row of the table, so it can exceed the octet rule. So 3rd row or below. So that's a potential Lewis structure. Now, it doesn't meet the octet rule, where we do meet all the octets in that structure. So based on the octet rule, we would say the structure on the left is the best one. But let's look at formal charge. Now, what I will encourage you to do, and at least until you get the hang of this, is we're going to start drawing the bonds for now as individual electrons, not as lines, so we can divide them up easier. So a single bond is a 2-electron bond. So I'm going to draw that as 2 electrons. And a double bond is a 4-electron bond. So 4 dots to represent that double bond. Okay. Now we're going to divide those equally. So that was the second statement up here. The bonding electrons were shared equally between the bonded atoms. We ignore electronegativity. Oxygen is more electronegative than sulfur. So oxygen has a stronger attraction for those electrons in that bond. They aren't shared equally. But in terms of formal charge, we're going to divide them up equally. Okay? So of the double bond, 2 electrons go to oxygen, 2 to sulfur. Of the single bond, 1 to each. All right. Now, what we're going to do is we're going to count, say for oxygen here, the electrons around that oxygen. And we're going to count 6. And we're going to compare that to its normal valence. Okay, so look at oxygen in a periodic table. It's in group 6, so it has 6 valence electrons. We counted 6 electrons in this structure. They're the same. So the number of electrons in the structure match its normal valence. That means that oxygen has a formal charge of 0. So we're going to put the charge in parentheses to distinguish this from, say, a full charge on the molecule. This is a formal charge. Okay? So if the number of electrons assigned to the atom in the molecule matches its normal valence, then the formal charge is 0. Let's compare that to the oxygen on the right, okay, where we have 1, 3, 5, 7. So again, its normal valence is 6 for oxygen. We have 1 extra electron in the molecule, an extra negative electron. 7 electrons versus 6. An extra electron, that would be a -1 formal charge. Or we might just show that, rather than writing a 1, we might just put a negative. Okay, but -1. All right, what about sulfur? Oh, and you probably have caught this already. I forgot my lone pair on sulfur. I started to count electrons. I'm like, sulfur doesn't have enough there. All right, let's try that again. So again, we copy down from the structure that we drew. Okay, and sulfur is also in group 6, so it has 6 valence electrons. What does it have in this structure? 1, 3, 5. Okay, so as an atom it has 6. In this structure it only has 5. It has 1 less electron. So we take an electron away for that structure. This would be a +1 formal charge. Okay, that's all there is to it. So if the electrons in the molecule match the normal valence, that's a formal charge of 0. If you have extra electrons, in this case for this oxygen on the right, we had 1 extra electron, that's a negative formal charge. If you remove electrons compared to the normal valence, then that would be a positive formal charge. And what do you notice about what the formal charges add up to? Yeah, they add up to the overall charge on the molecule, +1 and -1 and 0. This is a neutral molecule. It does not have an overall charge. All right, so the formal charges should add up. That's a good way that you can check whether you've done this right. All right, so there's our formal charges. Let's look at this second structure. All right, and I'm going to do the same thing, and hopefully I can draw my Lewis structure. I can transfer my electrons correctly. I'm going to put the lone pair on sulfur first. Double bond is a 4-electron bond. Okay, so I hope I did that correctly that time. And let's divide those up equally between sulfur and oxygen. Oops, sorry about that. All right, again, the normal valence for both sulfur and oxygen is 6. All right, let's count. Oxygen on the left, 2, 4, 6. Matches its normal valence. Formal charge is 0. What about sulfur? 2, 4, 6. Matches its normal valence. Formal charge is 0. 2, 4, 6. Matches the normal valence. Formal charge is 0. Now what you'll find a lot of times when you do have 0 formal charges, you don't write 0. It's only if there's an actual formal charge other than 0. Okay, so all the formal charges are 0. They do add up, of course, to this neutral molecule, as we would expect. So based on formal charge, we would conclude that the structure on the right is the best structure Okay, so best structure based on formal charge. So which is it? Based on the octet rule, structure on the left. Based on formal charge, structure on the right. So again, the best structure based on formal charge is the one that has formal charges closest to 0. Okay, and in this case, all three were 0. Well, to really make a determination, you would need experimental data. You would have to look at the bond lengths. If the sulfur-oxygen bond lengths are closest to double bonds, as we have in the structure on the right, you would conclude that as your best structure. If they're closer to a bond and a half, then the structure on the left would be better. But again, this is just one way of helping you figure out maybe which is the better structure based on formal charge. All right, let's do a couple more examples. In the Lewis structure video, part 2 that I recorded, we drew the structure of nitrate ion. So look back at that video if you'd like to go through that. And at that point, we just put the negative charge of the nitrate ion outside square brackets. And I mentioned in that video that we could assign formal charges and express the charges that way. Okay, so let's look at how we would do that. So again, there are 2 other resonance structures, but once we assign the formal charges, they're going to apply to any of the resonance structures. But let's go ahead and draw our bonds as dots. Okay, now we're going to divide them up equally between the bonded atoms. Divide up those bonding electrons. And let's do the oxygens first, because we know that oxygen has 6 valence electrons. So let's compare that. And let's look at the one on the right, 2, 4, 6. So that one's 0. We don't have to write the 0. Okay, but I'm going to write it there just for sake of argument. Let's look at the other 2 oxygens. Both of them have 2, 4, 6, 7. 2, 4, 6, 7. That's 1 more than its normal valence. So what is the formal charge of each of those oxygens? Yeah, 1 extra electron. Each of these is going to be -1. Okay. Now you might be thinking, we do have to add up to the charge of the ion, in this case, as a -1. So you could be guessing that nitrogen must be +1, but let's figure that out. Okay. So nitrogen normally has how many valence electrons? Take a look at a periodic table. Nitrogen is in group 5. So nitrogen, 5 valence electrons. All right. And so what do we count here for the nitrogen in our molecule? 1, 2, 3, 4. 1 less electron than its normal valence. That would be a +1 formal charge. All right. And so what we see is that our formal charges must add up to the charge of the molecule or ion. Molecules would be neutral. They should add to 0. This is an ion with a -1. We have -1 and -1, which is -2, and +1. Those add to -1. That looks good. So if we were to draw this out, one way that we could express, I'm going to go back to how I have this shown here. Rather than putting square brackets with a negative sign on the outside, I could show the molecule with its formal charges. I would put a -1 for each oxygen and a +1 for the nitrogen. And again, typically we don't put formal charge to 0, so I wouldn't label this oxygen on the right. And then we would see -1, -2, and +1. Overall, we add up those formal charges and we see that that ion has an overall -1 charge. So by doing this, by putting the formal charges, I don't have to put the molecule in square brackets and put the charge on the outside. Okay, one more example. Let's do another ion just to practice. Sulfate. All right. So let's go through, let's draw the Lewis structure here and see what we come up with. Sulfur, group 6, 6 valence electrons, 4 oxygens, each at 6 as well, group 6. 2 additional electrons for that -2 charge. And what does that give us? 32 electrons. 16 pairs. All right. Oxygen more electronegative. That'll go on the outside. Sulfur less electronegative in the middle. Make a pretty picture by connecting with single bonds. Complete the octets on the outer atoms first. All right, how's that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, that looks pretty good. Now, if we left it like that, we'd put square brackets with a -2. We're going to assign formal charges here in a minute. Now, let me just show you another structure. And again, this is quite often what we'll use formal charge to potentially predict which is the better structure. You will see sulfate ion actually drawn like this. With 2 double bonds. We know that sulfur in the third row of the periodic table can exceed the octet rule. So this is possible. Okay? And we have our same 16 pairs of electrons. Which of those is the better structure based on formal charge? Which is the better structure? All right. Now, one thing as you get better at doing these, we can just leave our bonds and let's divide these up. And we know a single bond is a 2-electron bond. Okay, so we know how, oops, I kind of missed that one, but you get the idea. We're going to divide that double bond. Same thing over here. Divide the single bonds, divide the double bonds. Get the idea. Okay, so let's look at the structure on the left. What's nice is if you notice that all 4 oxygens are single bonded oxygens. So they're all going to have the same formal charge. They all have 3 lone pairs of electrons and a single bond. So remember, oxygen and sulfur both have 6 valence electrons normally. For each of these 4 oxygens, 1, 2, 4, 6, plus 1, splitting that single bond, 7 electrons around each oxygen. Each of these oxygens is going to be a -1 formal charge. Sorry, that should be a 1. All right. And what about sulfur? Remember, we're dividing up the electrons of those single bonds equally. So 1 electron from each of these single bonds goes to sulfur. So that's a total of 4. It, as an atom, has 6. So we've taken 2 electrons away from it. Okay, 2 less electrons. Sulfur is +2 formal charge. Do they add up? -4 for the oxygens, +2 for sulfur, -2 overall. Okay, that's kind of a mess. Let me just kind of redraw that without putting all the lone pairs in. All right, and what we see for our formal charge, -1 for each oxygen, and +2 for sulfur. All right, let's look at the structure on the right. We just did singly bonded oxygens over here. So we have 2 single bonded oxygens, 7 electrons for each one. Each of those oxygens will be -1. All right. Now the double bonded oxygens we expect to be different. And if we count, 2, 4 for the lone pair, and then 1 electron each for the double bonds. Remember, a double bond is a 4-electron bond, so 2 electrons will go to the oxygen. So that oxygen has a total of 6, which matches its normal valence of 6. This oxygen has a formal charge of 0. You can expect that the other double bonded oxygen will be the same, and it is, formal charge of 0. All right, what about sulfur? Again, we divide the bonds up equally. So 1 electron from the single bond to sulfur, 1 electron from the other single bond, 2 electrons from the double bond. So let's count 1, 2, 3, 4, 5, 6. Okay. Now again, I encourage you, until you really get the hang of this, draw your structure with the bonds as dots and divide those up. But the double bond, 2 electrons, the other double bond, 2 electrons, that's 4. 1 for each of the single bonds, 6. Matches its normal valence. Sulfur is also 0. All right, so let me draw this again. If we do not put the formal charges of 0 on our structure, the only formal charges we would have to put, each single bonded oxygen is -1. The double bonded oxygens are 0, the sulfur is 0. So, a lot of work. The conclusion in this case would be that the structure on the right with 2 double bonds is the best structure based on formal charge. All right, so even though sulfur exceeds the octet rule, we would say that that is the better structure. The structure on the left we would say is a better structure because in the sense that it meets all the octets. Now, again, we're going through this exercise here. You will get questions, which is the better structure based on formal charge? How would you really know? You would have to look at data. You would actually have to look at, what is a normal sulfur-oxygen single bond length? Again, that would be an average between many molecules. What is a normal double bond length? And what is it in sulfate? Okay. If it's really close to the average single bond length, then you would conclude that this structure is right. If it's kind of intermediate between a single and a double, then this would be the better structure. Okay? But we'll talk about, as far as class goes, what is the better structure based on satisfying the rules of drawing a Lewis structure, and what is the better structure based on formal charge. Okay? All right, I think that's enough for now. Have a wonderful day, and take care.